Hello and welcome back to the Hyperthesis episode 59. Today we're gonna talk about a bit of vacuum. My name is Pheely.
I'm Patrick. And I'm Liam.
Alright, so today we are to the episode 59, almost 60, which is kind of nice number, isn't it? Well, we're back today. So for the intro topic today, it's actually Liam told me about it, and actually I think we have heard about this for quite some time because since the James Webb telescope was operational and brought back new data, there might be some amendment to what we know, thing that we thought we knew for a long time as the fact, right? And the one important fact that we reference all the time, maybe not everybody, but that universe is 13 billion years old. And that is being challenged right now because the new data kind of doesn't agree with that.
Like 13.7 billion years old? Or something like that? Closer to 14, I think, right?
Yeah, 13.7, 13.8 around there. And the way they figured that out is through all the light that they captured, and they just postulate with the Big Bang theory, that the light that came into the detector is redshifted. You think of the Doppler effect when the ambulance go by you on the street. Even though the pitch of the siren is the same, it's like a flat tone, you can hear it's like the pitch difference when it's go past you. So it's higher when it's coming towards you, and a little lower or deeper when it's moving away from you. It's called the Doppler effect. And light has a similar effect we call the redshift and blueshift thing. So from the object that moving towards you and moving away from you, they have the shifting in their color.
The other thing about that particular age is that the astute listener will realize that relativity tells you that time is relative, right? So if we're saying the universe is 13.7 billion years old, someone else might see it to be different. But that particular time is calculated from if you go back and do all this inflationary cosmology, Big Bang mathematics, there's one particular reference frame, this absolute reference frame you can work in, where from that point of view, the universe expands in a completely isotropic way, which means everything moves away from you. Everything is separated by the same distance, and everything looks I guess like the matter I don't fully understand this, honestly. I probably shouldn't be talking about it, but I just wanted to point out that it's that particular reference frame where they calculate the age of the universe to be from. And then, like, I guess from Earth's reference frame, it's such a slight difference that we can just say it's 13.7 billion years.
Well, isotropy is one of the fundamental assumption, I guess, that no matter what direction you look at the system, the nature is the same, no matter which way you look at it. That's the isotropy, right?
Yeah, I guess
And
that might be the wrong word. I think I mean like the fact that the universe expands and somehow from this particular frame, everything is moved away from it at like the exact same rate and distance. Next episode I might come back with a more researched comment on this, but I just want to point out that the age of the universe comes from this particular reference frame, this absolute reference frame, based on the Big Bang.
Well, I get it though, because we only have very little what's it called, detector, right? It's us. We don't have the sample from different part of the universe. We just have one. It's around here, right? It's not like we put on detectors on the other side of the universe. So the reasonable thing is to assume that other parts of the universe should work the same way. That well, if it's expanded to here, if I picked out the outer part completely different in the universe, they might have the same physics, and that could be true or could be not, right? Like it's really fundamental assumption, but we can see some evidence to it where physics work pretty much the same way everywhere on Earth and even in space, right? The physics, the law of gravity is consistent. So I think there's some assumption you could make a lot about that. But so the point is that, well, the James Webb Telescope got the data from early universe galaxies, and what they found is that this, what they call quote unquote the impossible early galaxies were found, where the galaxy appear more mature with the components that evolved that look like there have been galaxy for such a long time. But the age of a galaxy, they from the redshifting, from the calculations, or they found that it's not, well, it's not that old. So how come we think it's, well, we find these mature galaxies when the redshift tells you it's not that old? So either that galaxy doesn't have that mature thing, or mature evolution is kind of wrong, or the factor we use to calculate the from redshift to age of universe or age is off.
Okay, so the James Webb is seeing galaxies that formed in the early universe, because the James Webb effectively sees backwards in time, right? Because all this light has been traveling through after the Big Bang and inflation. All this light's been traveling through space for a very long time, and the whole point of the whole point of the James Webb telescope was that you can now see this light from further away where other telescopes couldn't. So they're seeing galaxies that, according to our current models of how galaxies form, should not exist. Right? Is that the point?
Well, it should not exist with those components. Let's say I'm not sure what the components are. Let's say like you are a grown man, right? Like, and we have grown man features. And but if I tell you that you are only 5 years old, that doesn't make any sense because you are a grown man. That's what we found. Like James Webb
Mm-hmm.
looked over to the early universe and said, "Well, you look like a grown man, but the age says you're 5 years old." It's
Yeah, the
like, well,
galaxies, they're older than they could like, according to our current models, they shouldn't be able to look this old. They should have.
yeah, because
Yeah.
they say if you look into the past, right? So these are early galaxies in the universe, so they shouldn't have the features of an evolved galaxy that's old, but they do. So maybe it's the fact that those galaxies are actually old, and we just assume they're young. Maybe they're not 5 years old if they have the characteristics of the the mature galaxy. Maybe they're much older. And then if they're much older, but they're the quote unquote early, maybe the universe is older. That so to accommodate that features. So I think the professor in University of Ottawa, Rajendra Gupta, proposed this concept that the universe age to be 26.7 billion years to account for that impossible early galaxy prediction. And the paper actually went into details about it, and it actually went into the evolving physical constants, which was, I think, proposed by Dirac. That
Hmm.
The physical constants, coupling constants, are not really constant. They evolve throughout the evolution of the universe. And they also touch onto the tire light theory or hypothesis that was rejected quite a bit. That, oh yeah, light just lose energy traveling through the universe. That's why we see these type of observation. But there are a lot of evidence against that. So tire light might not be the best candidate.
I guess I don't know much about the changing physical constant thing, but I guess maybe like in the early universe during inflation, when the universe formed, for whatever reason, the laws of physics formed as well in a particular way. But maybe they just like maybe gravity maybe in the early universe gravity wasn't the gravity we see today. Maybe for like a second or something it was different and these constants changed, and I don't know. Or maybe he mean like they changed over time, or does he mean like in this Big Bang there was like a little bit of changing, or does he mean like over a longer time period? I don't know.
Well, Dirac proposed that the gravity, the constant of gravity, gravitational constant decrease over time, right? Which is a bold claim. It's like, well, maybe the gravity just was much stronger. It's losing its um, losing its power over time. But that's kind of strange thing to propose. To well, it's not that strange really, but it's like, well, it's really hard to measure. Like, well, uh, are we in the more stable part of gravitational, what's it called? Gravitational constant now? Who knows?
So, just one thing I want to mention with this discussion is the fact that we can't see all the universe, including some very large objects that are out there. And we're now kind of recognizing that there are these very mature galaxies for their age, or galaxies that are making us rethink the age of the universe. But there are also other things beyond our visible sight that have made us rethink things in the past as well. And one of the big things, literally, is called the Great Attractor. And this is a massive, massive something that's estimated to be, I think it was over a million times or millions of times more massive than the Milky Way. And the supercluster that the Milky Way is a part of includes about 100,000 galaxies. And when we look at these redshifts using telescopes like James Webb Space Telescope or other telescopes, we're actually able to see that there's slight variations in the redshift, and those slight variations add up to essentially everything within the supercluster moving towards what's known as the Great Attractor, which we can't actually see, partly because it's obscured by the galactic plane of the Milky Way, but also because things are too far away that light hasn't reached us yet, and it might never reach us.
Well, the other thing I want to point out is that, well, the two things that came to my mind when Liam talked about before, like things are similar or like the same everywhere in the universe. That the one evidence to support that is the cosmic microwave background. That's like no matter which direction you look, it's pretty much the same. So that's one of the key evidence that we have on that. And the other thing I want to talk about, well, not talk about, to mention is that the redshift, the word redshift, is kind of misleading because James Webb is infrared, so it's under red. So redshift means it's going up, right? But in fact, redshift is the other way because it's redshift and blue shift. But if you start from not visible, from infrared, redshift, you're going towards red, but which is not true.
I think this again, I always get confused with reference frames sometimes, but I think this kind of preferred frame I mentioned before, I think it's actually the frame in which the cosmic microwave background looks the same in all directions. Whereas like we see it have very, very slight fluctuations. I think this reference frame from where you get this, 13.7 billion year calculation of the age of the universe, I think that's the reference frame in which the cosmic microwave background in that reference frame is perfectly homogeneous. There's no fluctuations in it. So, so do you guys think that the universe, so that this new proposal to explain the fact that these galaxies that we don't know how they can exist in the state they do, the proposal that the universe must be about twice its current age, or twice the age we originally thought. So like what, 26, 27 billion years old. Do you think that's the case? Because I remember watching some stuff on this when it was new news, and a lot of people said like it's a nice idea, but they're not convinced. They think there's other things happening.
Well, I'm not really convinced that the Big Bang Theory is the theory that describes the whole truth either, right? I mean, there's a lot of skeptics, and also like well, here's the thing: we just don't have enough evidence to convincingly say it happened for sure. That's the thing. That's like cosmology in general, right? You try to fit all these evidence and data with one model. That's, hey, here's how universe work. And I don't think we get to the point where we can say for sure things happen. Maybe soon, because James Webb now we have so much more data, and maybe someone will come up with some wacky idea how universe work, but fits everything really well. So I think now we get to the point where we can start making new theories from these new observations that I think much more what's called inclusive in terms of like scientific observation than what we ever had in human history. Like the James Webb Telescope gonna tell us so much that I'm not sure anymore going forward what's gonna be the age of the universe. Is even gonna be the Big Bang? Maybe it's gonna be different now.
Yeah, I think our current theory of inflation and like the Big Bang is there's other ones, but the Big Bang is like the most popular one. I agree. I don't think the universe it's probably not twice as old as we thought. I mean, maybe it's a bit older, maybe it's a little less old. But I think that yeah, our current theory of how the universe formed is definitely not complete. And once you figure out that, it would account for these galaxies probably. I mean, it's easier said than done. But inflationary cosmology to me is just like archaeology. Like imagine you're trying to study some civilization that they're all dead now. They're not, you can't ask them like, what did you do to build this building? You have to kind of reverse engineer all these like subtle clues that are left and like kind of paint a picture of what it was. That's like inflation. Like we weren't there to see what happened. So we have to kind of piece together what we see now, reverse engineered, and kind of make an educated guess on what happened.
And the harder part is to like we only have light to deal with, right? Like we don't have order or like the EM. Oh, now we have gravitational waves.
Yes, now we got gravity waves. That's the big one too. We got the James Webb, and we have gravitational waves now. So this is like a great time to be a cosmologist and an astronomer, I think.
And archaeology, at least you can dig up something and look at it, right? Like here's like, well, we are this like lowly little dot in the universe. We just try to take in as much as possible.
I will say, maybe one day, I'm not confident with it, dark matter as well. That might be a nice thing if and should it exist in the form that we think it is.
Well, yesterday was Dark Matter Day, November 4th. So here we go.
I didn't even know that was a thing. I watched this semi-famous physicist called Neil Turok. He has a very interesting theory on dark matter involving neutrinos. So I might present that in the future. It's really cool. Anyway, we should probably move on, I think, right, to the main topic.
All right. So I think it's a good time to transition to our main topic. So our main topic today is, I think Liam is on the QFT fever right now, the quantum field theory fever, which I don't know how that happened. I think it's got to him. It got to his head and latched on and breathed into his brain. So now he's the QFT guy. Anyways, so Liam's going to be talking about false vacuum decay.
Yeah, I'm not a real QFT person. Some of the people I work with are real QFT people. I just talk about it a lot. It's like quantum gravity. I talk about quantum gravity all the time, but I don't actually do it. So yes, false vacuum decay, which like Pheely said, I'm actually going to give you a little QFT primer before I talk about what that is. Which, like, we talked about QFT before, and it comes up every now and then. So quantum field theory, which I will call QFT from here on, or I'll try to at least. It's a theoretical model of the universe that combines classical field theory, special relativity, and quantum mechanics into a single framework. It's kind of QFT and its sub-branches are our most successful theories yet. But again, QFT, it works really well, but not with gravity. Gravity, as obvious as it is, I drop an apple and it falls. It turns out it's the most difficult one to deal with when you try and merge it with quantum mechanics. Quantum field theory, it models both massless and massive particles by so-called quantum fields. So everywhere in the universe, you can imagine that there are these so-called quantum fields that exist and permeate through everything. So therefore, even in the vacuum of space where there's nothing at all, it's not completely empty because these quantum fields will exist there. So the vacuum of space isn't actually completely devoid of energy like you might expect. It has these invisible quantum fields there that have some vacuum energy.
Was that ever measured?
Yeah, I think
Or
so
can it
there's
be measured?
this thing called the vacuum catastrophe. I kind of forget the details, but I know that this vacuum energy, there's a few things that you can't actually describe with regular quantum mechanics or regular relativity if you don't have a vacuum state. So
Yeah, I
the
thought
fact
the
that
vacuum energy is assumed rather than directly measured.
yeah,
It works
so
well when you put it in, right? Like,
there's problems with it. There's this thing called the vacuum catastrophe, which is related to it's like quantum mechanics and gravity don't agree. There's this whole thing with it. I don't really remember the details, but so for example, the Casimir effect. There's this effect where if you have two parallel metal conducting plates next to each other in the complete vacuum of space, there'll be a force between them. They'll attract each other, and you can't actually. That's something you can measure, and it has been measured, and you can't take into account that force unless you have a vacuum. So you have these unless there's these quantum fields that fill the vacuum. The other thing too is that in an atom, imagine you have like a hydrogen atom. There's a nucleus that consists of a proton and a neutron, and then there's one electron that orbits it. If you excite this electron, you can fire a photon at the atom and make this electron have higher energy. The electron will spontaneously jump back down to its lowest energy state after some time, and it'll emit out a photon in the process. You need quantum field theory to describe how this thing jumps between states. You need the actual presence of energy in the vacuum to
so
do
you're
that.
saying QFT basically solved laser, right? Lasers, well, it does,
Yeah,
right?
like you can
some
describe lasers.
laser, how you pump lasers like that.
Yeah, I think like you can describe lasers without QFT, and that's like probably what the original theory was. But you kind of have to you use this knowledge that it jumps between states. You excite it, and then after a while, it spontaneously decays back down. But that spontaneous decay can't be explained by regular quantum mechanics. Like, why does it do that? You need quantum field theory. So, yeah. Coming back to that, so quantum field theory, it's our best theory. It works really well. It matches experiments super well, but it has some problems, which is why it's not the complete theory of everything. We're still working on it. But this lowest energy state. So imagine you have a vacuum with nothing in it except these quantum fields. The lowest energy state of these quantum fields is rightly called the vacuum state, where there's no obvious massive particles or like photons whizzing around. There's just nothingness. So you won't see this invisible vacuum state, but it's there, and it has this smallest minimal energy. It turns out quantum field theory tells us that the particles that we actually see in nature, like photons or electrons or protons and whatever, they each have their own associated quantum field with its own vacuum state, and excitations in this vacuum state manifest as the particles themselves. So, for example, imagine in the vacuum of space, there's no particles, but there's something called a photon quantum field. So it's the quantum field for photons, for particles of light. It will exist in the vacuum, and it actually has these random fluctuations. But if you add in enough energy to this vacuum state, so let's say, like, imagine there's some process you can just pump energy into it. You'll actually you'll amplify these fluctuations, and you'll create a photon out of the vacuum state. So the particles excitations in the vacuum state are the particles that we see. That's what quantum field theory describes. the particles are excitations in their respective quantum fields. So you have all these different quantum fields. You have like the electron quantum field, the photon quantum field, whatever. They all kind of overlap and are everywhere. And if one of them gets excited, then say that's an electron. So the electron in front of me now, that's just an excitation in a electron quantum field.
Well, when you say pump energy in, what do you mean energy? You mean putting like force in, like feel? What do you mean by energy?
I don't know. I'm just imagining like imagine you can add some energy to it. The way I think of it is that I'll come back to your comment in a second, but the way I think of it is like when you look at the surface of the ocean, imagine you're on the shore and you're looking into the ocean, and it looks really flat. You don't see anything at all. That's that's like my analogy to the vacuum of space being empty. It looks empty. The surface of the water looks flat. But if you get close enough to the shore and you look at the water, and maybe it's a particularly windy or rainy day, you'll see that there's all these small random waves on the surface of the water moving in all directions. That's kind of like the random fluctuations in the vacuum state of this quantum field. And then if you take a stick of dynamite and throw it into the water, it blows up and it makes a huge wave in the water. That dynamite's adding energy to the system, and this large wave kind of like it overshadows these small oscillations from the wind, and that would be like a particle. As
Well,
far as
is
yeah.
it's easier to think of like something that's like physical as energy, right? Like because well, what we deal with in daily lives are two things, right? Like the kinetic energy and potential energy. But to me, it's hard when I try to wrap my mind around the energy in terms of quantum systems, because like it's not like you can. Well, sometimes they're like Hamiltonian. It's the same way we have kinetic part, right, and there's potential part. But when you talk about this kind of fluctuation, you pump energy. Like, what do you mean energy? Is such a mathematically it made sense, right? It's by construction is made that way. Here's what we call energy is a abstraction of the ability to perform work or to perform motion, right? But is it like that in quantum field? Because like when it's a field instead of let's say an object or wave, energy. What is it? Energy? What is energy?
Yeah, that feels beyond my pay grade to answer. It's a deep question. I
When you
guess the
say
way like
field is like a mathematical field, right? Like when remember group theory, we have field.
no,
Is it
no,
that
not
kind of field?
no. It's not a group. It's not a mathematical field. It's like I guess when you think of a classical field, think of like an electromagnetic field. A quantum field is it's when you, mathematically it's if you take that classical field and you quantize it, which is like a fancy way of saying you now have creation and annihilation operators in it. And yeah, I don't really have a good physical intuition of it. I guess when I think of energy, I think of like, the famous E equals MC squared. Like energy is just something that can be converted between different things. So like a photon has an energy, but it's massless. But there's this thing called the Schwinger effect, where if you fire enough photons, so you have a strong enough electromagnetic field, it'll actually excite these quantum vacuum fluctuations into actual massive particles that travel in opposite directions. So you're like converting energy to mass. There's stuff like that.
Well, let's tune in back to episode 500 in the future when we figure this out and have better idea of what's going on, and we'll tell you what energy really is. 500.
Yeah. Like I admit, I'm not super knowledgeable on some of this stuff I'm talking about. But
So what is
I know a
this
little bit about
false
it.
vacuum and false vacuum decay?
Yeah. So, hold on. Yeah. So overall, let me just ground myself again. All these various quantum fields for these different particles, they overlap mostly everywhere in the universe. I mean, maybe you can argue on the inside of a black hole, we don't really know what's going on, and I won't get into that, but they give rise to all the particles that make up all matter which we see and all the forces which these particles experience, which is again mostly true, but gravity, dark energy, and dark matter are kind of like this asterisk on that comment. They're still elusive. We're going to ignore them for now, like good physicists. And if these quantum fields behaved even slightly differently than they do, the very universe that we know could not exist. So we're pretty lucky to exist at all because physics ended up being the way it did for whatever reason. However, just because we think that the vacuum of space is a very special state in its lowest possible energy, that does not mean it's true. Just because we see it to be the lowest energy state, that doesn't necessarily mean it is. It could be a metastable state, for example. So false vacuum decay describes this. It's a theoretical model of cosmology that explores the possibility of our universe actually existing in a metastable state. It's based on the idea that the current vacuum state of our universe might not actually be the true or most stable vacuum state. So we've talked about metastability before, but the idea is that in nature, things want to exist in their lowest energy state. So if you have a ball on the top of a hill, it has a very high potential energy. And if you give it a chance to, like you give it a slight horizontal push, it'll roll down that hill to its lowest possible position that it can achieve. It'll minimize that potential energy. And like I said before, actually, for the electron, that excited electron in a hydrogen atom, if you increase its energy by some amount, after some time has passed, I think it's a quite small amount of time actually, that high energy electron couples to the quantum vacuum and it jumps down to its lowest energy state. So things want to be in their lowest energy states, and that's related to entropy and stuff, which we've talked about, and I don't know enough about it to get into it, and I don't really want to get into it. Yeah, so things want to be in their lowest energy state. So what if if we live in a vacuum that's not truly the lowest energy state? What happens when it jumps to that lowest energy state? If the vacuum state of space itself is metastable and not the true vacuum state, what happens? If this were to be the case, there's a chance that our universe could undergo a catastrophic event. Very bad.
I want to point out that, when you say lowest energy state, that's not zero, right? I think when people think about, vacuum, people think of nothingness, right? The thing is a zero. But rarely we find things that are zero in nature. Like most things, I can't think of things that, if we don't count like counting, 0, 1, 2, 3 integers, there are very, very few things I can think of that's like has a value of zero.
You do a lot of
yeah.
A lot of these energy is kind of this relative thing too, right? Like in physics, you'll often define zero energy, but it's relative to something, so it's not truly zero energy. It's like I can't think of a good example right now that's intuitive and doesn't involve like a 10-minute explanation, but yeah, so when I say the minimal energy state, I mean like a finite greater than zero energy, but it's smaller than if you excite it. So like I guess the ball on the hill, at the top of the hill, say maybe it has like 100 joules or 10,000 joules of energy, potential energy, gravitational potential energy. It reaches the bottom of the hill, it now has 100 joules of potential. It has zero. It'll have zeros. Yeah, it'll have 0 joules of potential energy relative to the top of the hill. But then also you can imagine, well, it's still on a hill. It's above sea level. So relative to sea level, it'll have some finite energy. So it's all relative. It depends what you define as the 0 point.
Yeah. So why can't we normalize everything with the lowest possible energies? Let's say call it zero.
Yeah, I think quantum mechanics. So in quantum mechanics, you imagine like a hydrogen atom. That thing has a minimal energy state. The electron orbiting it does, and that's some finite energy. And I guess you can't go lower than that unless you like alter the system or change something. I don't really know.
So you're saying that zero is kind of okay. It's abstract, right? Like then because the physical world doesn't manifest at zero. However, it is possible. That it could not have that energy, but in the physical world, it always have some kind of energy, even though zero it's a mathematical concept of nothingness, right?
Yeah,
But
I
but since we
don't
are not
know.
live in nothingness, well, this is getting more metaphysical. But
Yeah,
since we are
I
not living in nothingness, right? There must be some what's it called, like
Mhm.
constant point of energy or something. Maybe not energy. That's not zero. Because zero to me is a fascinating concept. Like, well, why don't we define everything as zero in terms of at the vacuum? Right? Start from zero. Why start from one? Why start from 1.2?
yeah, I don't know. Like this I don't think about this kind of stuff very often. I'm not gonna lie. Like the vacuum states and how that works. I think about vacuum states a lot, but not so much like the is there such thing as a zero energy ground state? I guess again it's all kind of relative, right? But because this is our universe we're talking about, it's kind of like the biggest it's everything. When we say the universe, we mean typically like everything ever that we know of. Unless you're one of those people who studies like parallel universes and stuff, but I'm not going to get into that. What were we talking about? I've lost track. We were talking about the vacuum
Oh,
state of a
yeah.
universe.
So what is false vacuum?
Yeah, so this false vacuum decay proposes that the vacuum that we see, so if you look in empty space, you see nothingness plus these invisible quantum fields. So I guess you don't see them, but you kind of know they're there through experiments and theoretical models. Um, According to quantum field theory, maybe it's physically something different that we have yet to understand. But false vacuum decay proposes that the vacuum that we see in our current universe is a false vacuum. It's not the true vacuum. And we just happen to exist in it. So, what if this is the case? It turns out that, I mean, the whole universe could end if we're in a false vacuum. Yeah. If the universe is in this metastable state, according to classical physics, false vacuum decay would only occur if you added a very large amount of energy to the false vacuum to perturb it out of its metastable state. So, how do I word this? I'm trying to think of an example. I guess my example is always quantum tunneling, which is this very interesting phenomena where if you have, how do I describe this? Imagine you have a very thick cement wall. If you run at that wall, you'll hit it and fall down, and maybe you'll have a nosebleed, but you will not pass through the wall unless it's a very weak wall. Imagine this is like a very sturdy, invincible wall. You won't pass through it if you run straight at it. So you're not going to Harry Potter into a different place through the wall. But quantum mechanics actually tells you that there's a finite probability for you to pass through this wall. This is quantum tunneling. So if you hit the wall, matters both waves and particles. This quantum wave has a small probability to tunnel through the wall, and you will appear on the other side. Assuming that you're a quantum human and you obey the laws of quantum mechanics. Typically, quantum tunneling is with like electrons and single particles, but this is just like a fun analogy. So, even though that probability might be very, 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 very small for a human to hit a wall and pass through it, if you have infinite time and you run at that wall over and over and over and over again, you will pass through it eventually, given enough time. So false vacuum decay is the idea that even though classically, if we lived in a metastable state, classically, it won't spontaneously become a false vacuum. It won't. Let me reword this. If we live in a false vacuum that's not the true vacuum, classically you'd expect. I guess we're probably safe, right? Nothing's gonna happen unless you do something wild and I don't know, set off, can like have like bajillion supernova at the exact same point in space time. As long as you don't put a ton of energy into the system, you will stay in the metastable state. But because we live in a quantum world, there's a small possibility that the false vacuum can tunnel to the true vacuum, and the universe could end because of that. It would change the laws of physics as we know it, and we're very lucky to exist because of these very particular laws. So if they change even a little bit, things could end. That's kind of the idea of false vacuum decay.
Well, I think someone talked about this before. Is it lucky? Because there are these are all possible things that could happen. But it's not. Because it's not happening. So it's not really, like, we don't see it. It's not really possible. We are here. What's it called? It's like this logical fallacy. It's not because okay. It's not that the universe is like that because we are here. No, it's the opposite. We are here because all those things happen. So like that, we wouldn't be here if that didn't happen. But we are here, right? So that's the fact that we know we are here, and we looking out. It's like here, and this is why these happen. Like maybe they say like, oh, there are billions of the possibilities. Well, we are lucky to have this one. It doesn't matter if there's a billion of the possibilities. Those things didn't happen, right? So I'm reluctant to say that like, oh, it's lucky that these happen. It's not luck. It happened, and we then use our mind to abstract that there are all the possibilities. So that's my kind of hot take on it.
It's a hot take. I still think we're lucky to exist, but anyway. So if false vacuum decay, so if we don't live, if the vacuum of space we see isn't the real vacuum of space, it's only this temporary vacuum that exists, what happens if it tunnels to the true vacuum? So once the decay is initiated, it'll happen at a specific region of space-time somewhere in our universe. This bubble will form, which is the new vacuum state. This bubble contains what is the new vacuum. So it basically it forms within this new universe, this universe of this new vacuum. This bubble expands outwards at the speed of light. So it actually moves through space-time at the speed of light because it can't travel faster than that. And as the bubble expands, it engulfs all matter and energy in its path, converting it to the new vacuum state. And this newly formed bubble, it'd actually be the new universe, and everything in it would obey different fundamental physics. Since if you change the vacuum state of our current universe, physics as we know it changes. So like this vacuum state, it's required for these electrons jumping down from different energy states in a hydrogen atom. So now that you've changed that vacuum state, that process is going to change fundamentally, and then all of chemistry changes. The periodic table is no longer the periodic table, and that's just like an atom. Imagine what it does for everything else, right? So it would be this catastrophic universe-ending event. But will it happen? So even though this is a theory, do we think it'll happen? We don't really know, right? Many people believe it will happen, though, because direct calculations based on the standard model predict that the lifetime of our universe's current vacuum state is about 10 to the 65 years. So I don't think you and I have to worry about it. So as a reference, the universe is like 10 to the power of 10 years old. So they think...
No. For a reference, our lives is all 10 to the 2 years old, max.
Yeah, yes. So if humanity can manage to live a very, very long time, which I have my doubts, but this calculation they've done, they predict with 95% confidence that in the next 10 to the 65 years, and again, it's probability, so it's not saying in 10 to the 65 years this will happen. It's saying like within 10 to the 65 years, with 95% confidence, a false vacuum bubble will form somewhere in our universe. A single bubble will form. Again, this is all based on the standard model and quantum field theory, which we know are not fully complete theories because they don't work well with gravity. So if those theories are wrong, they can be modified. Maybe this calculation changes, but that's kind of our current understanding of it. So they're pretty, these calculations, they're quite confident that we actually do live in a false vacuum right now based on the standard model.
Well, I think I want to lead back into what I said about, this evolving physical constants that Dirac thought about, that a lot of physics or scientific systems or theories are hinge on the fact, or like they relied on this idea that theories are like don't change, right? Things don't change, right? Like for example, you find out how gravity works, and should that is how gravity should work in the past and in the future. And if we can find that one way that gravity works, you found out have some equations to describe it, and we can describe the entire universe. But it's also possible that the rules in the past and the rules in the future are going to be different from the rules now. Like I said before, like what if gravity was much stronger in the past? It's getting weaker and weaker at a rate that we don't know. I think it leads back to like, well, how about the vacuum as we know? As like Liam said, we live in a false vacuum. But has it always been false vacuum? Could the theory, are the theory then dynamically evolve as the universe progress, or are all the laws stay the same? Because the physical laws, I mean, there's no reason that wouldn't change. I mean, there's some evidence that it has been the same for a long time, but is that true for every law?
I want to believe that the physical constants don't change, but that's mostly like a selfish reason. It's mostly because the physical constants have changed over time. It makes physics way harder for the cosmologists.
Right? Like everything like scale is gonna be so hard to figure out if the physical constant change. Let's imagine this is if light is slower relative to speed of light now, right? Like it it would mess up everything, and then you have to measure how the maximum speed of light changed throughout history, and it's gonna be crazy. It's like adding another level of, when you do calculus, you do first derivative, second derivative. Now you have to have fourth derivative to figure out what we have, right? Because there's another layer of change, rate of change we need to figure out that just come from physical constant changing.
Yeah, it would be really interesting, but it would also it would be one of these like we have to rewrite our theories now kind of things, which we need to do at some point because we're really struggling with gravity. One last thing I want to comment on, and so false vacuum decay. Currently, people think it's going to happen, but I think anyone listening to this, you'll be long dead before that happens. So I don't think we have to worry about it at all. Unless you figure out how to become immortal, then maybe you'll have to worry about it. But yeah, but even if like it happens soon, even if false vacuum decay happens soon, there's actually this like kind of safety net that we have, which it's the fact that the universe is expanding. So we know the universe is expanding, and the distance between galaxies is actually increasing. And eventually, it's going to be the rate of distance between galaxies becomes faster than the actual speed of light itself. So everything we see, all these distant galaxies we see, eventually they'll fade out of view because they're moving away from us faster than the light that they emit can travel to us. And again, that's not for a long time. Like, our sun will go supernova before then, probably, but we don't have to worry about it. But if a false vacuum bubble forms somewhere, so imagine somewhere really far away in our universe, this false vacuum decay happens at a particular region of space-time, this bubble forms and it starts firing out and changing the universe as we know it. If that happens to be outside of a specific radius of our current galaxy, we don't have to worry about it because the expansion will mean that anything moving at the speed of light will never reach us, and the bubble moves at the speed of light, so it would never reach us. So it's kind of like this. It's kind of like the expansion of the universe stops small errors. I don't know. Maybe that's a bad way to think about it, but it would protect our galaxy from false vacuum decay.
All right, I think that's quite a topic, right? So we went through QFT, tiny bit of it, and then we talked about vacuum and energy states and what we think is. I think this episode is also quite involved, right? It's quite a lot to take in, and I still don't really truly understand vacuum. I think it's a strange concept, but okay, it's reasonable, still strange, right? The way it's set up, just like, oh, here's, well, what growing up we think of as there's something called nothing out in the universe, and somehow nothing is not nothing. Nothing has this specific energy level that we can beautifully and rigorously carved out theories that describe what we know in quantum fields and with particles, light, and interaction between matter and object and things. So it's a wonderful theory.
Yeah, it's this theory. I mean, it kind of like drops the vacuum drops out of QFT. It's this natural thing that comes out of it, and you need it to describe a lot of things, I guess. Not a lot of things we've experimentally tested, but a few of them. But you definitely need it for our best understanding of physics that works to date. Like even the reason why I want to talk about false vacuum decay is because in my field of analog gravity, people have started studying it. They've started studying inflation because we only have one universe. We only have a system size of one, which if you ever do experiments, you know is very bad. You want a big system size. Means more data, means less uncertainty kind of thing. So they figured that if you can make things that mimic our universe in a lab and study them, you might learn something about our current universe. You can actually like test the dynamics of it. You don't have to do this cosmology, archaeology stuff. You can actually like see things happening. But anyway.
All right. So I think that's a good point to move on. So today, before we get to the story, which Patrick is going to be talking about the history of vacuum. So he's going to be telling you how to contact us and where to find us.
Well, if you would like to contact us, especially if you're an expert in vacuum decay or would like to discuss really anything to do with that, or quantum field theory, or really any type of science, you can reach us through multiple different methods. We have an email, we're hyperthesispodcast@gmail.com. You can send us an email with questions, comments, queries, concerns if you have concerns, or suggestions for future topics.
Yes, I'm almost sure I said something wrong talking about the vacuum and vacuum energy today. Like I feel like I did. A lot of it is correct, but I think I must have misspoke at some point. So like if you have concerns, please tell us and we will correct them.
Yes. You can also tell us your concerns or corrections over Instagram. You can find us at the Hyperthesis, where you can DM us. We also post updates about when we're posting the show, such as the first one that just went out of this season. You'll also find other updates, especially when we take breaks, of when we'll be back. And there's usually some funny content on there, such as Pheely holding a turkey this past Thanksgiving. You can find us on YouTube. We have our first 4 seasons fully up on YouTube, so you can watch it, you can share it with friends, you can have it playing in the background, or watch the mesmerizing animations that Pheely put together. You can also find us on pretty much any podcasting service that exists, whether it's Audible or Spotify, Apple Podcasts, Google Podcasts. You can find us wherever, you can share us wherever, and if possible, feel free to give us a rating, subscribe to us, download us, send us carrier pigeons, however you want to contact us or get the word out about the podcast. So, again, if you are an expert in your field, we would love to have you as a guest. We've had a lot of grad students as guests on this show. And again, if you are an expert in quantum field theory or really any area of science, we would love to have you on. Now, going to today's story, we spent a lot of the main topic talking about false vacuum decay and what would happen there. But for the story, I want to go over something a bit simpler, something maybe less nuanced, but still hard to think about for those that have to deal with it. And that is a vacuum itself. Now, I'm not talking about the device that you can use to clean your floors and everything. However, that does work on similar principles to some of the things I'll be discussing, but the idea of a vacuum itself and how we can actually achieve vacuums. So the idea of a vacuum has existed for many millennia, originating with thought experiments from well-known Greek philosophers like Aristotle and Plato. They theorized that a vacuum, or a place in which there is a void of all material, was impossible. This is because the surrounding denser material would fill that space instantly, so there would be no time for a vacuum to form, and therefore it could not exist. And Aristotle even suggested that the motion of an object through medium without any resistance would continue forever. And he used that in defense of vacuums not being able to exist. But it's quite funny that he said that because that's kind of a precursor to Newton's first law of inertia. So it's kind of funny that he used his argument of how vacuums couldn't exist to explain essentially a very important law within physics for many hundreds of years. Now, the first known vacuum attempt was by Hero of Alexandria, who failed to create an artificial vacuum way back in the 1st century AD. And the idea of this Aristotelian non-vacuum, or that vacuums couldn't exist, really clung on. And the idea of a vacuum was rejected by many years by all kinds of different scholars. Now, a vacuum was first theoretically suggested by a Muslim mathematician called Ibn al-Hittam, who showed that a vacuum was the imagined 3D void between the inner surfaces of a containing body, which, again, relates to kind of some modern ideas where there's, for example, a lot of empty space in an atom, as people say. Now, using ideas of a vacuum and ideas that there's this kind of empty space within a container, a suction pump was actually developed by Arab engineer Al-Jazari in the 13th century, and later in the 15th century, Europe started implementing that idea as well. Now, the departure of philosophers and scientists from the Aristotelian view went to the supernatural explanation of a void, and in this case, they theorized that a vacuum was a void found beyond the cosmos, and this idea was widely acknowledged by the 17th century. Other great thinkers have also thought about the vacuum, including René Descartes, and other thought experiments pondered how vacuums could be created. So one suggested that if you had two touching plates that were exactly in contact with each other and pulled away quickly, perhaps a vacuum could form between those two. However, it was thought that this was unlikely and that, once again, vacuums would go against nature itself. Now, this is a fun experiment you can do to try and replicate this experiment. Instead of using two plates, you can use a glass bottle filled with some sort of liquid, preferably one that's not carbonated. And if you tap the top of that glass bottle while holding it, you'll actually form a vacuum underneath. Now, it's a partial vacuum, and you might very well break the glass, so do this with caution. But what you're doing is essentially the same idea as separating these two things, since when you bump the bottle, it moves the bottle, but not the liquid within inside it, and that forms a vacuum in which a lot of vapor will form quite quickly, but for an instant you have quite a good vacuum. Now, going back to the 17th century, experiments were actually beginning to show that at least a partial vacuum could exist. Torricelli's mercury barometer of 1643 was able to create a partial vacuum inside of a glass tube. Now, this was done by filling a tube that was sealed at one end with mercury and then inverting it into a pool of mercury, causing a partial vacuum to be formed on the sealed end as the mercury dropped. And what he discovered was that you could actually tell what the atmospheric pressure was like based on how large that vacuum part of the tube was. And this today is what we know as the first barometer, and some units from it are still used because we know that at sea level, or average atmospheric pressure, can be measured in millimeters of mercury, which in this case, at atmospheric sea level is about 760 millimeters of mercury. Now, not long after Torricelli, in 1654, Otto van Guericke invented the first vacuum pump. With its invention, he was able to pump air from two copper spheres that had been pressed together with grease between them, but not glued together in any way, and then demonstrated the strength of atmospheric pressure by getting teams of horses to try and pull the copper spheres apart. So he was able to pump the air out from between these copper hemispheres that were just touching, demonstrating the true atmospheric pressure and its power. Now, after that pump that was designed by van Guericke, Robert Boyle and Robert Hooke developed a better vacuum pump. But after that, the subject was pretty much left alone for the better part of 2 centuries until 1850. Now, during this time, in around 1850, Heinrich Geissler invented a mercury displacement pump that was able to achieve a pressure of about 10 pascals, or 0.1 torr. Now, the unit torr was named after Torricelli, and again, 760 torr is typical atmospheric pressure, which is about 101 kilopascals. And for reference, a kilopascal, or just a single pascal, is 1 Newton per meter squared. Now, from this invention by Heinrich Geissler, rapid advancements in vacuum technology led to decreases in the record low pressure over time, reaching values as low as 10 to the minus 6 torr by 1894. And it almost happened in a linear trend from 1850. So there were these advancements that just kept decreasing and decreasing the vacuum pressure that could be achieved. Now, these newer vacuum systems used liquid piston pumps instead of solid piston pumps, and were really quite complicated systems because we didn't really have electric pumps like what we have today. Now, these techniques start to reach manufacturing levels, such as those to make the light bulb, which were used by Edison to try and improve the incandescent light bulb, which requires a vacuum to actually function. Now, molecular drag pumps were like the Fosbury flop of vacuum pumps, which were first introduced in 1913 by Gaeta. Now, this used the movement of air molecules against a rotating surface to direct gas from a high vacuum side to a low vacuum side. And it utilized the fact that this rotating surface would cause molecules or atoms to essentially drag along them, which would move them. Now, this was truly pivotal as we were able to get a tenfold increase or tenfold decrease in vacuum pressure, giving a pressure of around 4 times 10 to the negative 7 torr. And this, again, was a huge moment. And around this time, we also saw the introduction of what were known as mercury vapor diffusion pumps, or diffusion pumps, which also used oil. These had no moving parts and utilized the movement of vaporized oils or mercury and could reach a lower limit of 10 to the negative 8 torr. Now, many high vacuums nowadays use what are known as turbopumps, which are rapidly rotating turbines relying on electricity that force any particles that come towards them away from the high vacuum side to a lower vacuum side. However, at the pressures that we're dealing with these turbopumps, it depends on the mean free path of the particle. And with fewer particles present, it's just kind of random chance that will actually make it to the turbopump and then be forced out of the chamber. And in the case of these turbopumps, say if the vacuum were 10 to the negative 9 torr, then the mean free path of a particle can be up to 40 kilometers before it actually collides with another gas particle. Now, at this point, properties of matter must be considered when you're making a vacuum chamber itself, as gases can pass through what seem like solid materials and cause an influx of gases, limiting your vacuum capabilities. Now, the lowest pressure that we can typically achieve today within super high vacuums or ultra high vacuums is 10 to the negative 13 torr, while the lowest vacuum that's been recorded indirectly is 5 times 10 to the negative 17 torr, which was measured at 4 Kelvin, or the temperature of liquid helium. This corresponds to about 100 particles per centimeter cubed, so not a lot at all. However, in parts of deep intergalactic space, there may be as little as 1 hydrogen atom per meter cubed, which is an insanely high vacuum, much higher than what we can ever produce on Earth. And even on the surface of the moon, we get about 4 times 10 to the power of 5 molecules per centimeter cubed, which, again, is quite good. It's about 10 to the negative 11 torr, but intergalactic space is incredible in that it's so empty. But of course, then we get into issues with vacuum fluctuations, and is there a vacuum? What's going on in a pure vacuum like in intergalactic space, which we are still figuring out. Now, vacuum gauges and measuring how low pressures get and all that is another story for another time, but hopefully this was a nice little low pressure situation.
Nice. I just wanted to ask, what's a Fosbury flop?
Okay, so for people who are into sports, especially track and field, there's the high jump. And traditionally how people did the high jump was they would like try and get their full body over it and like kind of split their legs or like stay upright and just jump over the bar. And then Fosbury, he did the Fosbury flop, it's called now, where he essentially went backwards over the bar and people were able to get a lot higher with it. And it was kind of this pivotal moment of, oh, we can actually do a lot better if we change the technique.
Okay, I'm not a track person, so explains why I don't know it. Anyway.
Well, that was great sportsmen do, right? They changed the game, right? Like it's crazy how like the best of the best, they would always like change the rule, have to like nerf them basically. So they're not too good.
Yeah. Same in physics, right? Like, Einstein comes along and all these quantum and relativity people, and they blew everyone's mind.
All right. Anyways, thank you, Patrick, for the enlightening story. And I guess we'll see you guys next time. Take care.
Bye, everyone.
See ya.